n, but there is a 1 over n, so it's of order 1. So this term is of order 1. This term instead, since, well, I have all the lambda alpha that are here, which are far from lambda 1, as long as lambda 1 is a distance of order 1 from all these ones, can be neglected. This is of order 1 over n, and this one, if you remember, it's of order 1 over square root of n. Okay? So I will just forget this term. Yeah. Sorry? At the beginning, they're at 0. Then they will start to move. But as long as there is a finite distance here, this term is subleading with respect to this one and to this one, so I will just forget it. Yeah.
Why is it order 1? Like,
this one?
Like at t equals 0, the spacing is 0.
Yes. So, okay. So the spacing is 0. So exactly t equals 0 is slightly singular. But then at t equal epsilon, they will be spread over a length which is of order epsilon.
Yeah, so shouldn't it be like 1 over, like, I don't know, something about the time?
Yes, sorry. You're right, sorry. What I meant by order 1, I meant with respect to n. So you're right, it's of order t. It's of order t. Actually, more, it's of order square, we'll see, it's of order square root of t, actually, we'll see. But what I wanted to say is just, I was just looking at to the factor n, because I consider n large. Was the question? Okay. So we just wanted to say that when n is large, this one will go. And so what I wanted to say is that I have an equation here for these n minus 1 eigenvalues in which I can forget that there is this lambda 1. So if I can forget that there is lambda 1, here, this equation that I have here is just the equation that I would have if this term wasn't there. So I know what's going to happen to these ones in time. So if I plot what happens in time, so I know that this n minus 1 will form a semicircle like this. We'll have a density, rho of lambda, for this n minus 1. And then, well, here, with the equivalent of sigma square at time t. So at time t, you have sigma square, which is equal to t. I have just some many g in such a way that at time t, I have sigma square. So here will be a semicircle of which has a left edge and the right edge, which are plus minus 2 square root of t. Is it clear? Yes?
Just to clarify, the calculation we did yesterday was valid for all n, right?
Yeah, and now I'm working at n large. N large, yes. Is it fine? So I'm just using the fact that, well, at time t, so all these are spread like in this way. Now there is lambda 1, which is different. So let's write the equation for lambda 1. So we'll have d lambda 1 dt, which is equal, here I have 1 over n, sum over beta different from 1, of 1 over lambda 1 minus lambda beta. And then again, well, then I will have plus eta 1 of t. But actually, again, this term here, if I look, this term is of order 1. And this we will see in a minute, it's a deterministic term. This term here is of order 1 of square root of n, and is stochastic. But when n is large, so at least for lambda 1, I can forget about it. So when n is large, I can forget about this term. And the equation for lambda 1 is this one. And so this is when n go to infinity. And let me write again what is the equation for lambda 1. Yep.
Why do you get a semicircle there? Even though you don't have the quadratic term?
Because I don't have the trapping term because I don't renormalize. So I'm just adding small Gaussian random matrix. So after that, I add, let's say, at time t, I add some, a lot of matrix in such a way that the variance of the matrix at time t is t. So sigma square is equal to t. So this is why I have a semicircle that is growing.
I see. Okay.
Yes?
It's not clear to me why we neglect here the stochastic term while previously we didn't.
Okay, because here is, so here we can, because the equation, so you see, the big difference here is lambda 1 is a finite distance from this one. So indeed, you will have a deterministic motion plus very small fluctuation, but I'm after this deterministic motion. In this case, I have eigenvalues which are typical distance 1 over n. And if I want to study, the dynamics of two closed eigenvalue, then I should consider the term.
A question about the stochastic process. Are we assuming that n lives 0 is just the spike? Like,
Yes.
where is this? Okay.
Yeah. All right.
Can I go back to Francisco's question?
Yeah.
Why isn't there the quadratic potential there?
It's just because I constructed the in this way. So what I said is that my matrix at time t equals, so at t equals 0 is just VV transpose rho. And then at each time, what I do is that I add the G. So this at time dt. Then at time 2 dt, there will be VV transpose plus, let's say, G1 plus G2, and so on and so forth. And before yesterday, I was always renormalizing also. So I was adding G and normalizing in such a way that the variance at each time remain the same. Here instead, I want to construct the matrix M progressively.
I see, and that term was there because of the normalization.
Yeah. So when n go to infinity, the equation for d lambda 1 is going to be d1 da1 dt. And now this one is the sum over all the other eigenvalues. I can rewrite with the density of eigenvalue, which is d lambda rho lambda. So rho lambda, okay, let me write this way. Rho lambda 1 over lambda 1 minus lambda. Now, what is this? This is the semicircle law. So it's going to be 4t minus lambda square divided by 2 pi t, if I'm correct. Yes? So, okay, so this is it's an integral over lambda. You can do it, and if you do it, we are not going to do it. I mean, it's just an integral. You're going to get that you have a closed equation, so you do this integral. You have a closed equation which is d lambda 1 dt, which is minus lambda 1 t minus square root of lambda 1 square t minus 4t, no, this is a plus, divided by 2t. Okay, so I have an equation, and we will see this equation will tell me that actually the eigenvalue which is here will increase in some way as a function of time. So here I have, if I plot time, what I will see is that this eigenvalue will increase. This one also, since there is the semicircle, they will increase. I don't know how to put them, but okay, they will increase in this way. They will be all here. And now I want to know what is the law of this eigenvalue as a function of time. And I'm not going to solve, but I just give you the answer so that we go quickly. So this is, I have to solve this equation with the initial condition that lambda 1 in 0 is equal to rho. And the solution is very simple, even though the equation looks not very nice. Is lambda 1 of t is equal to rho plus t divided by rho. Simple. So now we can plot as a function of time what happens to lambda 1 of t. And let's call it this one. It will be lambda 2 of t. So it's the upper edge. So it's the left edge of the semicircle. So we know what lambda 2 of t is doing. So lambda 1 of t is this. And lambda 2 of t is equal to 2 square root of t. It's just how the semicircle is growing when I add all the g. And we know that we want to arrive at t equal 1. At t equal 1, we have reconstruct the matrix. And so we want to know, well, what's going to happen. So let's start. So we have rho. Lambda 1 is here. It's at rho equals 0. Maybe I can use 2 color. So I have lambda 1 and lambda 2. All right, lambda 2 start from here. And so at t equal 1, so let me try to draw it in it's equal to 2. This is just 2 square root of t. This I can erase now. And now the other one, which is rho, so it's just linear. You see, it's rho plus t divided by rho. So if rho is larger than 1, what I'm going to get is something which is like, so okay, let me do it. So if I start, Let's say that I start here. Here this rho is very large. And then what I'm going to get, I'm going to arrive here. And this value here is rho plus 1 over rho. This is the value at equal 1. Now, if I decrease rho, what's going to happen is that this slope is actually going to increase. And this value actually is going down. So what you will get is something like this. You can draw it yourself. And then when you're here, which corresponds to rho equal 1, you will touch here. So because rho plus 1 over rho is going to be equal to 2 when rho is equal 1. And then if you go below rho equal 1, you are here, then you will get something which is like this. So you will touch B4. So at rho equal 1, we have a transition. So when rho is larger than 1, so let me now draw the density of eigenvalues of the matrix plus the spike.
So here, rho is the constant that is different from the density, right? Not the same.
Sorry? Rho is a constant. It's not problem.
What is the like the meaning of behind this constant rho?
So this is, well, so I am adding a deterministic matrix, which is a rank 1 perturbation, to the random one. So rho is the strength of the rank 1 perturbation, because it's rho times VV transpose, and so it's a projector times rho.
Okay, I see.
Okay, so now what we have is that when rho is larger than 1, the density of eigenvalues, rho of lambda, is going to be the semicircle between -2 and 2. And then here you have an isolated eigenvalue, which is at rho plus 1 over rho. Whereas when rho is less than 1, you just have -2 and 2, and that's it. There is no isolated eigenvalue. Which is what, Remy already anticipated yesterday, well, in another context. Now, there is something else that is very interesting, and which is make all these things useful in many fields, is what happens to the eigenvector. So the idea is that this rank 1 perturbation, you can think is really some structure that you have in the matrix, and then you perturb it with a random part. So what you want to know is whether this eigenvalue that you have here, it still has some information about the original vector. So what you can show, and we are not going to do it, but you can show that V1, when rho is larger than 1, is going to be equal to V, which is my original direction, times square root of 1 minus 1 over rho squared, plus 1 over rho, times, let's say, a part which is perpendicular to it. Whereas instead, when V1, in this case, when rho is less than 1, I mean the V1 dot V, so the scalar product of V1 over V, it's of order 1 over square root of n. So, well, it's almost orthogonal. So here, you really have this phase transition. It's signal versus noise. So this means that if rho is large enough, so if the signal is strong enough with respect to the noise, even if it's perturbed by the noise, it remains at the end. So you can see it in the density of eigenvalues, and you can find that the eigenvector still points a little bit in the right direction. So if you think here, so you had this direction, which was the direction V, and after a certain time, in this case here, you will have that V1 will be around here with a certain non-zero projection on V. Whereas in this case, well, you get this is V, and V1 is essentially orthogonal to V. Now, this transition is interesting because it happens in many different fields. Okay, it will be interesting for us, but it happens in physics, biology, and also in machine learning and data science. So you can find it for example, in problems like when you look to another kind of, like the Wishart matrix that Remy discussed yesterday. So you look to data correlation matrices, and you can find that data correlation matrices can have a bulk which is random, and then they can have spikes like this eigenvalue that comes out. And in general, this carry an important information. And I'm sure that at least some of you have seen, if you study the Hessian, for example, of deep neural network, you can do a theory at initialization of random matrices. This was done, I think, originally by Pennington. And then you can study what happens after training at convergence. And also, it's much more complicated than what I'm telling you. But also in that case, you find a bunch of eigenvalue that comes out that seems to carry important information. So, okay, so this ends all the things I wanted to tell you about random matrices. Again, random matrices I think are useful in many different fields, in particular in machine learning. And there have been indeed cute results, at least in, for example, for Hessian, and I know that there are people here working on this, Hessian in deep networks. So what I now want to do is to start to discussing dynamics. So first, other questions on this?
What happens if you make the perturbation of high ranks?
So if you have a finite rank, I mean, essentially, they don't, I mean, if it's finite rank, they don't see each other. So you will have row 1, row 2, row 3, and it's going to be the same. If it's that the rank is, let's say, it's of order n, then it's more complicated. It can be studied. Again, you can always do it with this Dyson-Brownian motion. It just means that instead of starting from a few and 0, then you will start to many, and then you carry the Brownian motion. It is studied in random matrix theory. Other questions? Okay. So let's do now. Let's do the first study of dynamics. Okay, so what I would like to do in the dynamics, well, is that, so as you know, I mean, when you study modern problem in machine learning, you are typically in very high dimension. High can be, I mean, for example, in certain deep networks can be trillions, so a trillion of parameters. And the dynamic, when you study dynamics, gradient flow, gradient descent, stochastic gradient descent in this very high dimensional space, I mean, there are many things that don't work at all like you are used to in finite dimension. And so what I would like to teach you are, well, some idea and some methods which I think are important to try to treat these cases. And we will try to go from, let's say, more simple models to more complicated models. And it will be a little bit like what Nati was, for example, today. He got a lot of intuition from the matrix completion case. I will use other models, but the idea is the following. So try to push, I mean, the frontier of what we can do, starting from simple model to more complicated model. But you will see, in order to be able to analyze them, we will need to construct some new ideas and methods. And this is what I'm going to do. So today, I will just start with a very toy model, which will be a way to introduce some concept, show you already some non-trivial things, but also discuss that if you want to be serious and study, let's say, high-dimensional non-convex problem, we should do much more. Okay, so the problems that we're going to study, it's what I would call matrix PCA, and it's very much related to what I just discussed. So the idea is the following. So imagine that I have a vector v, which is the same that I had before, and what I get is vi by vj, and I get something which is corrupted by noise. So I will denote it exactly like, well, almost like before. I'm sorry, I'm changing notation. So we'll have a gij, and then I have a term here in front, which is n divided by rho. So this is the matrix that I will get, mij. And so the idea now is that, so this is the signal, this is what I get, and I want to retrieve v. So what could I do? Many things, actually, and this is a very simple problem. But so what we are going to do is, so the gij, the matrix gij will be GOE, as we studied. Rho is the same rho than before, and v is different, so the norm of v is going to be equal to square root of n. It's not 1. Just change notation because it's, I would make the connection with some physics literature, but it's the same problem. Okay, so one way to study this problem, which again is, you can do many things. The first thing that you could do is a spectral method. You just diagonalize, and then you see if there is one eigenvalue that pops up, and then you study if there is an eigenvector, exactly what I discussed before. But you can do also something different, which is you construct an energy, which is defined like sum over L and M of MLM minus XL XM squared, where x live on the sphere, sum over I xi squared is equal to n. And then you minimize this energy with respect to x on the sphere. Okay? So this is like doing the maximum a priori estimation. So it's not the bias estimation, it's the maximum a priori estimation. But you can also think in a very simple way. Well, you know that the matrix constructed by this plus a random term. So what I'm going to try to find is the best approximation to this matrix in the form XL, which is in the form, let's say, XX, which should be what I should get if there is no noise. Okay? And in order to do this, I will use gradient flow, starting from a random initial condition. So I take a uniform initial condition on the sphere, and then I'm going to do x dot equal to minus grad of E on the sphere. And you will see that this is related to the spherical spin glass that actually Remy discussed, I think, in the first lecture. And you will see that in dynamics is simple, but I mean, there are a few interesting things to discuss. Okay, so let me just study a little bit more the energy. So if I develop this energy, so the energy, and I consider the only part that depends on x, you see that if I take the square of this, okay, this is not dependent on x. If I take the square of this will give me a term which is of the form sum over L and M xL square xm square. But since sum over L xL square is equal to n, well, this doesn't depend on x because we are on the sphere. So the only term which is important is the cross product. Okay. So the energy, the only term which depends on x in the energy will be and also I will put in front here just because it's useful. Again, since I'm taking a minimum, I can put any constant I want in front as long as it's positive. And so here, when I take the cross product, I will have minus sum over L and M, MLM, XL, XM. I have, XM. I have a factor of 2, and then I have a rho divided by 4n, which then becomes 2n. Okay. And so if I now replace m by this, what I'm going to get is minus sum over L and M. So I have a first term, which is the Gij. So it's going to be 1/2 XL GALM XM. And then I have another term, which is minus rho divided by 2n, sum over L and M, XL XM BL BN. Which, let me write again, is minus 1/2 sum over LM XL JLM XM minus rho divided by 2, and then I rewrite this term like n sum over L XL B of L divided by n squared. So if you see now what is this, and then now I just, I don't put all the terms which don't depend on x in the energy.
So can I just ask?
Yeah.
So I mean, especially after you write it like this, you're literally just trying to maximize the Rayleigh quotient. You're just looking for the top, like you are doing PCA,
Yeah.
except you're doing it by some like non-linear algebraic.
Exactly. Yeah.
And the goal is to understand the dynamics of
Exactly.
conditioning in a
Yes.
situation where you know what you're
Yes.
going to get.
Exactly. Yep. Other questions? Is it fine, the energy? Okay, so now this term here, it's a kind of spin glass term. It's a simple spin glass that you studied already with Remy. But it's simple because x live on the sphere. And then this is a deterministic term in the energy. So you can think that you have an energy landscape in which you have a simple competition between a kind of disordered part, deterministic part. So the deterministic part, if you forget about this, what it will tell you is that x should be in the direction of v, which is the right answer. But now, because there is this one, well, that's not going to be, it is going to be corrupted, so the energy landscape will be changed. And so, well, you don't know whether, for example, the ground state, the global minimum, will be associated to v or not. And so what we are going to do is to, again, to solve this problem, we are going to do gradient flow. And we are just going to study what kind of dynamics we have. Again, in this case, I mean, this is just stupid to do gradient descent on the sphere, but we know already the answer. You just do the spectral method. But the idea is to see what actually the dynamics is doing, because it will be, I think, a guide for more complicated problem in which we have, I mean, it's a very complicated rough landscape. Okay? All right. Okay, so first thing is, so we have this energy landscape, and let's study this energy landscape on the sphere. It's not so simple. You could think that it's a simple convex landscape because the problem is so simple, but it's not true, actually. There are a certain number of critical points, and yes, the landscape is not convex. So let's study the critical points to understand how is the... So maybe what I can say is that, in a sense, in a nutshell, I'm doing in a very simple case something that we would like to do more generally. So in many problems in machine learning, you would like to know how is the energy or the loss landscape. Are there many bad minima, some good minima? And then you would like to know, well, once I know this landscape, okay, what the dynamics is doing in this landscape. And then can I understand what are the time scale, and so on and so forth. In this case, you will see it very simple, and then we will try to go progressively to more complicated case. Okay, first, critical points here. Well, it's very simple. You have to study the critical points, so when the gradient is 0 on the sphere, so the gradient on the sphere equal to 0. So what you have to do is, you know, since you have this, you are on the sphere. So this means that you have to add a constraint. So you have to do the gradient with the constraint that sum over I xi squared is equal to n. So the way to do it is that you have to add to the energy a Lagrange multiplier, which enforces this constraint. And now the gradient equal to 0 on the sphere. It becomes the following equation. It's going to be dE dxi plus lambda xi equal to 0, with the condition that sum over I xi squared is equal to n. Okay? And you have to find lambda such that this is verified. So let's take what is dE dxi. Well, it's very simple. Is here. So let me see which one. So I hope it's okay for you. I'm going to change the notation. So I'm going to define the m twiddle in such a way that, so m twiddle will be equal to rho n m, in such a way that the energy is going to be minus 1/2 sum over L and M xL m twiddle xm. And so m twiddle is just equal to J, is exactly the one that I defined just before in plus rho, I think, V transpose, if I'm not mistaken. Yes. Okay. So it's the one that I defined before, that we studied before. Okay, so now if I take the derivative with respect to xi, then I'm going to get minus sum over m of ml, sorry, yes, this will be L, mlm xm plus lambda xl equal to 0, with the condition sum over I xi squared is equal to n. Okay, so this is the equation for the critical points. I have to find all the x and all the lambda that verify this equation. Now, I'm sure you guess what these are x and what are this lambda. So if you stare 10 seconds at this equation. So what will be the critical points? So how many critical points do you have? So how many solutions do you have of this equation? Yeah, these are just the eigenvalue equation. So what you're going to have is that x critical points. So you have, so let's say you have alpha. Okay, let me see. Given if you have one eigenvalue, which I will call, if I use the same notation than before, it's going to be V alpha. And then I have This is the eigenvector. This is the eigenvalue. If I have V alpha and lambda alpha, then the solution, the corresponding solution, will be x equal plus or minus square root of n V of alpha. So this will be, there will be two critical points associated to this, and lambda will be just equal to lambda alpha. Okay? So what we have found is that we have 2n critical points in this energy landscape. And they are associated to the eigenvalues and the eigenvectors. And now I want to do something which is also what you would like to do in models like more complicated models, again, like in, for example, in deep networks. I want to study the Hessian. What is the Hessian of these critical points? And then we try to understand, to relate their Hessian to the dynamics. So the Hessian, in order to compute the Hessian of these critical points, what you should do, well, is the Hessian, again, you have to remember that you are on the sphere. So you should do, well, if you have a critical point here, indexed by V alpha, then you should do, well, you should move on the plane, actually, I mean, the coordinate given by the plane when you move along here and do the Hessian. So this is a very simple, I mean, differential geometry computation, so I will not do it. You can do it later, or we can do it together. But the Hessian, H around the H of alpha, around the critical point alpha, it's a matrix, L and M, and this is just equal to minus MLM plus lambda alpha Kronecker delta LM. So this is what you would have, I mean, if there was no constraint to be on the sphere. And since you are on the sphere, you have this extra correction. It's okay? Okay, so now let's study what is the Hessian around all these critical points. Okay, so now, well, what we have, and maybe something which is important that you did not ask, but so this matrix is a matrix which is n by n, but clearly the Hessian is in the space which has dimension n minus 1. So what it means actually that the true Hessian is this matrix, and a minus, I mean, it's in the space which is orthogonal to V alpha. Okay, because again, here you have V alpha, and you move in the direction which is orthogonal to V alpha. I've lost everybody, or everybody's following very well? Okay. So I was saying that, so the Hessian, you are moving on the sphere. So it's the Hessian on the sphere, which means that one way to, I mean, it's on n minus 1 dimension. And so the Hessian, here I wrote an Hessian, which is a matrix which is n by n. So it couldn't be the true Hessian. So I say the true Hessian is this matrix evaluated in the space which is orthogonal to V alpha. Okay. Okay, now, while we know the MLM so has different eigenvalues that we call lambda 1, lambda 2, lambda n. So let's do this way. So let's do it for the critical point alpha. What are the eigenvalues of the Hessian? Well, I'm going to have this is the identity matrix, and I know how to diagonalize this one. So the eigenvalue associated to the Hessian will be minus lambda 1 plus lambda alpha, minus lambda 2 plus lambda alpha, so on and so forth. At a certain point, I will arrive at lambda alpha. So this one is not there because I don't have the direction V alpha. And then I have minus lambda alpha plus 1 plus lambda alpha until minus lambda n plus lambda alpha. So these are all the eigenvalues of the Hessian on the sphere for the critical point alpha, for the two critical point alpha. Okay, so now let's see what they are. So let's start with the, if I take alpha equal to 1, so the critical point which corresponds to alpha equal to 1, so lambda 1, so I will be the, so maybe I should, so lambda 1 will be equal to lambda max. So it's the maximum eigenvalue. I just denote in this way. So lambda 1 will be the maximum eigenvalue of the matrix M, and then lambda 2 is the second, and so on and so forth. So now for alpha 1, so if I apply this, I will get, well, the first one is not there. So it will be minus lambda 1 plus lambda 1, but it's not there. Then I have minus lambda 2 plus 1 lambda 1, minus lambda 3 plus 1 lambda 1. minus lambda n plus lambda 1. And well, and so what do you get here? Since lambda 1 is equal to lambda max, all these eigenvalues are positive. You agree? Because lambda 2 will be smaller than lambda 1. So this is positive, this is positive, this is positive. So it means that alpha equal 1, you have two critical points with the Hessian, which is strictly positive. So these are the global minima. You have two global minima. Then let's do, I don't know, alpha just number 2. So if I take alpha equal to 2, well, then I get that lambda 1. So I have that. So lambda will be equal to lambda 2. And now if I look at the eigenvalues of the Hessian, I will have minus lambda 1 plus lambda 2, minus lambda 2 plus lambda 2, but it's not there because there is not this direction, minus lambda 3 plus lambda 2, and so on and so forth. Now this one will be negative, and this one is positive, and all these ones are positive. So this means that this critical point is a critical point that has one direction in which it goes down, and all the other ones that I cannot draw, but I mean, it's because I have just a board and not a multi-dimensional board, but well, all the other ones, they go up. Okay, so it's just a critical point of index 1. And then, well, you see how it goes until when we reach alpha equal to n. And in that case, you get minus lambda 1 plus lambda min, minus lambda 2 plus lambda min, minus lambda n minus 1 plus lambda min. And now all these ones are all negative, which means that these one are these two global maxima. Yep.
Just to make sure I'm following. So I think you're saying it can be slightly reformulated. You're saying, okay, you found the critical points. To compute the spectrum of the Hessian, you can work in any basis you want. You just diagonalize M.
Yeah.
And then you have an orthonormal basis of eigenvectors, and on each one you compute the part of the Hessian that doesn't know about that direction.
Yes.
And you've just written down.
Yeah. So I'm just, yes, the idea is really, I want to classify all the critical points, and then the Hessian are the critical points, to show that, I mean, even though this problem is super simple, still you have a landscape which is non-convex, in which you have two global minima, two global maxima, and a lot of critical points, since n goes to infinity. I mean, with index 1, index 2, so this one will be like this, then there will be, for alpha equal to 3, you have two direction which goes down, and all the other which goes up, and so on and so forth. Okay? And then what we are going to want to study now is if we start from a random initial condition, well, the system has to move in this landscape and try to find the ground state, the global minimum. Yes?
Yes. So my question is, of course, it's very efficient here to use the Lagrange multiplier to enforce the spherical constraint, right?
Yeah.
Because then you get straight to the eigenvalue equation. But will you get the same result if you just project the gradients on the
Yes.
on the direction of the sphere?
Yes, yes. It's just that it was simpler this way. But yeah, you can just work on the sphere directly. Okay, so, well, in order to try to understand a little bit better how is the landscape, now let's think, you remember there is rho, whether rho is larger than 1 or less than 1, the statistical properties of this matrix M are going to change. So this means that the landscape is going to change. So let's study how the landscape is going to change, or the critical points actually of the landscape are going to change if rho is larger or less than 1. So if rho is larger than 1, so what you have is that M, okay, so this is for M, the density of eigenvalue for M is like this. You remember? We just derived it, obtained this at the beginning. So this means that the Hessian, if you think what is the Hessian, so you want to say what is this is rho of lambda. And now you want to plot what is the density of eigenvalues, rho, for the Hessian H. the density of eigenvalues that I have. So for the global minimum, or the two global minima. So what you have here is that, well, you have it here. No, it's sorry, it was here. So you have, what you have to do is that you take the semicircle, you just put a minus to all the lambdas. Well, the semicircle will just then turn this way, and then you shift it, so just turn this way, and then you shift it of this value here, which is the lambda max. So this means that the density of eigenvalues of the Hessian around the global minimum is like this. Okay, and actually, well, this one is not here because, well, you don't have it except I did something wrong. Okay, so it's strictly, so you have a well-defined minimum, which is around, so this, in this case, you have the x, which correspond to the global minimum, is going to be, there are two plus or minus v1, and here you can really think, so v1, you know that v1 is oriented in the direction v, so here is the direction v, v1 is oriented in that direction because we are beyond the BBP, what we call the BBP transition. So this means that, well, this landscape, of course, the disorder part has, I mean, corrupted the fact that there was a clear global minimum associated to the signal, but still, I mean, the global minimum is still partially in the direction of the signal. And if we look at the landscape around it, well, it's a nice landscape with all the directions which are positive. So it's kind of convex around it, just around. And then this is for rho larger than 1. If rho is less than 1, if you do the same, now you don't have this point here. You have just this. So when you flip, this is what you're going to get. And also, if you look at the, so this will be V, but V1 will be almost orthogonal. So in this case, the global minimum, which is a plus minus V1, has no relationship with the signal. So what changed in this case is that, so really here, because of the different signal to noise ratio, in one case you have a landscape in which you have lost any connection to the initial signal V. You have a global minimum because you have to have some global minima, but you see you have a global minima in which actually, which here is marginally stable, in the sense that there are many, many directions, so it's very flat, the landscape around it. Whereas here, instead, when rho is larger than 1, there is really one well-defined minimum, and here it's really stable. So now I will plot a caricature, which is really a caricature, and you should see why it's a caricature. I'm sorry, but so in this case, you could think that you have something like this. So it's clearly not like this because there are not all these local minima, but okay, I mean, just to give you an idea. So you have a random part plus a minimum, which reminds of the signal. And here you have something which is like this, in which there is some, well, minimum somewhere, but I mean, the landscape is disorder and it's nothing to do, there is no information on the signal. Okay?
Can I ask though, like, it seems like your picture for rho greater than 1 is pessimistic.
Which one?
Your rho greater than 1 picture is a little pessimistic because I think if you draw the same profile for the Hessian at the other critical points,
yeah,
there's like each of the saddle points is going to have a direction that flows directly to a minimum.
Yes, I agree.
Right?
I agree.
So somehow like you won't actually spend a lot of time following like
The
lines you don't want.
Yes, definitely. I mean, this is what we are going to study now, the dynamics, and you're right. There is this direction which is important. So I agree. This is a caricature in many ways. There are not all these bad local minima, and also, yes, on each critical point, you have one direction that goes down toward the correct thing. We will discuss this. Okay, is the landscape clear? So the idea now is, okay, you know more or less everything about, you know the landscape, how is the landscape? So landscape is non-convex, has 2n critical points. When rho is larger than 1, you can, in principle, retrieve the signal because the global minimum has a direction with the signal, but we are going to see whether the dynamics with gradient flow is able to do it or not. In this case, in principle, you are not able to do it because just if you do the energy landscape or as just forget about the signal, so you can do gradient flow, but it will sit in one minimum that has nothing to do with the signal. So actually, we are more interested to this case. Okay. All right, so let's do the gradient flow. So I'm going to do gradient follow and not gradient descent, but you can also do gradient descent, and I will cite, give you a reference to what happens if you do gradient descent in this case. Are there questions on the landscape, the critical points, or? No? All right. Okay. So you should try to imagine how is this landscape when, well, we'll try to discuss a little bit more. Okay, so let's do gradient flow. And this again is gradient flow on the sphere. So what we have to do is to write down so dxi dt, which is equal to, so this is going to be, so minus the gradient, which is minus sum over j of mij twiddle. I think it's a twiddle. I hope I'm correct or not. Yes, it's mij twiddle, xj. And then you have minus lambda xi, so I'm putting always the Lagrange multiplier to not making things difficult. And lambda will be dependent on time, and it will be such that sum over I of xi squared of t is always equal to 1 at any t. And we are going to study the limit in which n is large, let's say much larger than 1. And then we will study times which are smaller and larger than, well, they have a scaling with n. So just, yes, just a moment. So this, we are going to use some idea that came from, I think, a paper by Cugliandolo and Dean. I don't remember, and it's in the 90s. But actually, so that solve it when n is large. I mean, not exactly this model, but something very similar. But actually, this model is solvable at any finite n, because it's what in mathematical physics is called an integrable model. But we are not going to do it, but just telling you, if you want to know more, it can be solved exactly at any finite n. Yes, there was a question.
Why isn't this gradient descent? What's the difference?
Gradient descent is because when you do a finite step, and when it's continuous gradient flow. Okay, so I have here there is a plus, do you agree? The energy was minus 1/2 sum over x mx, so there should be a plus because this is, remember, is minus gradient of E on the sphere. Okay, so well, let's just solve this equation with this constraint, lambda of t, which is like this. So again, this is easy. This equation is easy if you go in the basis that diagonalize m twiddle. So this is going to be dx alpha dt. So now x alpha is just x along the direction alpha, which corresponds to a eigenvector alpha. And so this is going to be lambda alpha x alpha minus lambda of t x alpha. And I have initial conditions. Sorry, I should put it here. The initial conditions are such, well, xi 0 is it's a uniform random vector. With the norm, which is this one. And so x alpha of 0, if I change basis, is exactly the same thing. Okay?
But the individual components aren't uniform, right?
So yes, so as I discussed, I think yesterday, yes, the probability of P of xi 0 is going to be a normalization times a Gaussian minus ni size 0 squared divided by 2. I mean, for all practical purposes. Okay. All right, so this is the equation that we have to solve with the condition that lambda of t has to be chosen in this way. Okay, okay, that's going to be easy. Okay, the solution of this equation is, with this initial condition, is going to be x alpha of t, which is equal to x alpha of 0 times exponential of integral between 0 and t of lambda alpha minus lambda t prime dt prime. Do you agree? Because if I take the first derivative of this, well, I go and I take the integral goes down, I take the derivative of the integral, and we'll get lambda alpha minus lambda t times the same thing. And now I have a condition on lambda t that I have to fix, which is that sum over alpha of x alpha t square should be equal to n, which gives me the equation n equal to sum over alpha x alpha square z 0 exponential of 2 integral between 0 and t of lambda alpha minus lambda t prime dt prime. This fixes lambda of t. Okay, so now the first thing I want to study is first the limit n going to infinity first and t going to infinity later. Okay, so I want to study when rho is larger than 1 or rho is less than 1, I take very, very high dimension, and then I look what happens when time goes on. And maybe, okay. So first case is n going to infinity first. And then, well, then I can look at any time, but the time will always be, I mean, if it goes to infinity, it goes to infinity less strong. I mean, it's after n. So when n goes to infinity first and t is fixed, actually this equation is going to be to simplify a lot. Because I can rewrite this equation like 1 over sum over alpha, x alpha square, 0, divided by n, exponential to integral between 0 and t, lambda alpha minus lambda t prime dt prime. Now, okay, these x alpha are uncorrelated from the lambda alpha, okay, because, well, the eigenvalues are not correlated with the eigenvectors, and these are the component of the initial condition over the eigenvectors alpha. And so you can show, well, think about it, but you can show that when n goes to infinity, this concentrate around its mean. And what is its mean? So what is the mean of x alpha square 0? So I did a mistake here, actually. It was a 1 here. So what is the mean of x alpha square 0? It's 1 because this is one component. So yes, so the norm is square root of n. So I can replace this by 1. So let's do it. This is true when n goes to infinity. I replace by 1. If I replace by 1, here I have 1 over n sum over alpha, and here I have the lambda alpha. So this is going to be d rho of lambda, exponential of 2 integral between 0 and t of lambda minus lambda t prime dt prime. So maybe I should use another, not lambda, but eta. These are the eigenvalues. And so this, I know what this is. Well, okay, let me first write in this way. So now what is this integral? So what is rho of t, rho of eta? Huh? Go ahead, I mean, simple. It's the semicircle, right? Now, you could say, yes, it's the semicircle, but be careful. If rho is larger than 1, there is the isolated eigenvalue. That's right, but the isolated eigenvalue just count 1, and we are taking n going to infinity first. So it's not there. So this is going to be only the semicircle. So it's d of eta square root of 4 minus eta square 2 pi exponential of 2 integral between 0 and t eta minus lambda t prime dt prime. Okay, so now let's study this equation. So this integral here should be equal to 1 at any time. And so this will fix lambda of t.
permutations in the first term? With respect to x,
How-
x
how-
alpha.
Sorry, say it again.
So we average the two terms, but x alpha and lambda alphas.
Yes.
Normally,
Yeah, so I said first, when n go to infinity, all these things are going to concentrate. So the first thing I say that I can replace x alpha square 0 with its average.
Not averaging, it's concentrated.
It's concentration, yeah. Okay, so let's study this equation. So can I erase all this and just put a 1?
At late times, do we not need to be more careful about the initialization of the x in the sort of spike direction?
Yes. What do you mean late time? I mean, what do you mean late time?
So it seems like if we do have a separated maximum eigenvalue, then just replacing this with expectation of 1 might not work at late times, where like it is a very different sort of like it could be a very strong weighting, right?
Yeah. So I think it's a very good point. So this is why I said n going to infinity first and then t. But you're right that if you start to make t scaling with n in a way that we will discuss, then what you say are important. Then we have to care about the single eigenvalue.
If we make n go to infinity and then t, will we ever actually
No,
reach our spike?
No, never. So we are going to see it now. But okay, this is just, okay, well, I will comment this. In reality, for any large n, you will do it, but I mean, if you do just this, you won't. Okay, so let's analyze this equation. Okay, so maybe we can do it together. So when t go to infinity, okay, we have the equation which is 1 over the integral over dt square root of 4 minus eta squared divided by 2 pi exponential of minus 2 eta t. And then we have exponential of plus eta t, I think. Minus 2 integral between 0 and t of lambda t prime dt prime. And there is something else that I didn't tell you which is important and which I will put here, is that you can show that lambda t has a very nice interpretation, which is that it's equal to minus twice the energy at time t divided by n. Okay, so I will not, I mean, it's easy to show. You just take the equation of motion and you can show it, but okay, I will not do it now. I mean, I can do it later if there is time. Okay, so it means that this lambda of t is not just a parameter that it actually has a very important physical meaning. It's minus twice the energy. Okay, so let's see what happens. So do you have guesses on lambda of t? How is it going to go when t goes to infinity? What's the solution?
Can we solve this explicitly because the term bracket is the homogeneity function of the semicircular distribution?
Sorry?
The term is the bracket.
Yeah.
It's the homogeneity function of the
Yeah?
semicircular distribution.
Yeah.
And then I can just take the log and derive with respect to t. No?
Yes, even though for t going to infinity, it's, I mean, I think the cumulant maybe they are good when t is small, but well. So I mean, it's, for example, it's, let's see, when t goes to infinity, what is the leading term of this expression? These are sum of bunch of exponential. So what's going to dominate? The maximum value, right? So these things means that, so eta goes from 2 to minus 2. So the exponential that will dominate here is the one with eta equal to 2. So you expect that you have exponential of 4 eta. Then actually you have to be a little bit more careful because this integral, well, goes to 0 when eta approach 2. So you have a correction here, which is 1 over t to the 3/2 that you can compute. This is how it goes when t go to infinity, the first term. Okay, it's easy to get if you work just a little bit. So this means that lambda of t, well, first thing, lambda of t has to be equal to 2 when t go to infinity. In this way, Why? Because otherwise you see that if it wasn't, I say it has to be equal to 2 in order to match this 4 of t. Because if it was larger, well, it cannot be equal to 1 because you get something which goes to 0. And if it was smaller, these things will blow up, so it can be equal to 1. So there is just one choice. It has to be equal to 2.
But I don't understand how that fixes the fact that you have the correction coming from after the integral vanishes at ether. Doesn't lambda t have to account for that as well to compensate to 1? I mean, if I only balance the exponential, right, I just add 1 over t over 3 over 2.
If you just, so this is just to tell you how this goes. So then I want what is the limit of lambda of t when t go to infinity, which is 2. And then I can compute the correction, and the correction are related to this.
Oh, yeah, sure. Yeah, sure.
That's what you meant. OK. So what are the correction? Indeed, if you can show that the correction, it's easy. They are going down in this way. And why? Well, you can do it if you see that this term here, again, should cancel this. So first, you have this 4 that is canceled by the 2. Now this one should cancel this one because it has to be equal to 1. And then to cancel this, if you put this term here inside the integral of 1 over t is a log. And then the 3 over 4 is just there in order to get t to the power 3/2. Now, the thing which is interesting here is that if lambda t goes this way, this means that the energy, E of t, is equal to, now I have a 2 which is not correct. So let me see. No, OK, it's correct. I have E of t, which is minus 1 plus 3 divided by 8t. So what this means, and now I will do it on the right-hand side, if I plot the energy as a function of time, energy as a function of time, what I'm getting is that I start from a certain value, and then I will go down to minus 1. And I go down here with the power law. So no exponential relaxation, a power law, which is 3, it's of order 1, which is 1 over t. OK. This you can say, OK, so what? So let's think what is the energy of the global minimum? And what is this energy when rho is larger than 1 and when rho is less than 1? So the energy, if you remember, was equal to minus 1/2 sum over L and M, XL, MLM, XN. So this means that the energy divided by M of the global minimum is equal to minus lambda max divided by 2. Okay, just, I just take if when x is the global minimum is associated to the largest eigenvalue. So this is minus lambda max divided by 2. And now when rho is larger than 1, lambda max is equal to rho plus 1 plus rho, which is larger than 2. And when rho is less than 1, lambda max is equal to 2. Which means that when rho is larger than the 1, the energy of the global minimum divided by n will be equal to minus rho plus 1 over rho divided by 2. OK, sorry, I should write it somewhere else. So in this case, the energy of the global minimum is going to be minus 1/2 of rho plus 1 over rho, which is less than the minus 1. And when rho is larger than 1, so lambda max is equal to 2. And the energy of the global minimum is just equal to minus 1. So which means that here, this picture is not so surprising when you are at rho less than 1. When rho is less than 1. So when rho is less than 1, you remember the energy landscape has lost any information about the signal. And so the energy of the global minimum is minus 1. And what you see is that the gradient flow is bringing you, to the energy of the global minimum with, with a power law behavior, not an exponential behavior. And this power law behavior is related to the fact that, you remember, you have, at the global minimum, you had an Hessian, which has eigenvalue which were arbitrarily small. What is surprising is, well, what's happening for rho larger than 1? So for rho larger than 1, the global minimum is here. So let me say this is for rho less than 1. And now for rho larger than 1, well, maybe I can put it. We have the energy goes down. Here there is the energy of the global minimum divided by n. And the dynamics is here at -1. Again, with a power law, which is 1 over t. So it's not saying actually that there is a good global minimum here, which is related to the signal. Okay, so now let's see. So of course, there is one possibility is that you could say, well, maybe the system is never able to go to the global minimum. But of course,
greater than 1, there is no minimum related to the signal.
For rho larger than 1, yes. For rho less than 1, there is no global minimum related to the signal. For rho larger than 1, there is rho is the signal-to-noise ratio, so it's, yeah. But you know, while the space here, I mean, there are just 2 global minima, so how is that? I mean, it's, you know that if you were in finite dimensions, so not in high dimension, well, you have a space which has 2 global minima. Well, if you plot the energy as a function of time, there is no way out. You should see that it goes to the global minimum. And here it doesn't, but you will see it does. It's just that it does on a scale that diverges with n in a very slow way. So let's compute it. So let's consider now the case in which n is large but finite. Okay, now n large but finite. And let's rewrite the equation. So the equation was 1 over sum over alpha, x alpha 0 divided by n. And here we'll sum over all alpha except 1. So 1 is, so we consider a rho larger than 1. 1 is the eigenvalue which corresponds to the signal. And here I have exponential of 2 eta of t. And then I have one contribution, which is 1 over n, x1 squared 0, exponential of 2. And here you have the lambda max, which is rho plus 1 over rho. And here I have exponential of -2 integral between 0 and t of lambda t prime dt prime. All right? So I just wrote the thing that I wrote at the very beginning and just singled out the term which corresponds to the largest eigenvalue, which now we know that it carries the information about the signal. So now let's see how are these two terms. So this term, we studied just before. We know how it goes. It goes like 1 over t to the 3/2, I think, was. Exponential of 4t. This is how it behaves. It's of order 1 when n is large. This term here is quite small, actually, because this x1 square 0, it's a random variable of order 1, but it has a 1 over n in front. So this term here is 1 over n, something which is of order 1, and then exponential of 2 lambda max divided by t. Sorry, times t. And then all this is multiplying this term here. Now you see that you have a crossover. You will have a crossover when t is large. So even though, when t is large, if t is large enough, lambda max here is larger. 2 lambda max is larger than 4. So if n is large, at a certain point, this term will dominate over this term. So I will be able to forget about this term, and this equation will be dominated by, well, these terms times this one. Okay? So this will give me a time scale, an important time scale for the problem in which I will realize that there is one special direction. So if I compare the two, so I should compare this to this. Well, this I think you can just do it. You can compare the two, and you will find that the time, let's say t star, at which this one, so if t is much larger than t star, then this term will dominate. So the second will dominate. And t star, it's of order log n divided by, well, lambda max minus, it's lambda max minus 2. And there should be a constant in front, but that I'm not writing. Okay, so what this means is that then if t is much larger than t star, so the condition that fixed lambda of t is this time this, and so I will find that lambda of t, when t is much larger than t star, will be equal to, well, minus lambda max. Sorry, it's equal to, well, let me write directly maybe the energy. Well, okay. Lambda t will go to lambda max, so the true one, lambda max, plus exponential correction. So correction which are in, exponentially small correction. And which means that the energy actually will be equal to minus lambda max divided by 2 plus exponentially small correction. So now if I go back to this, to what I have here, so what this means is that this is true, but then at a time scale which is of order log n here, this curve actually will go down, and will go down to the true ground state. And this will be an exponentially fast relaxation. Now, why this relaxation is exponentially fast? Well, because you know the Hessian, we compute the Hessian around the global minimum, and we know that it's this way, it's done in this way. So all the directions are strictly positive, so you will converge exponentially quickly to the global minimum. Yes?
So why did you get stuck in one of the other cases?
Exactly. So now the thing really to discuss indeed why we get stuck if we really get stuck. So indeed, so this is the thing that I really wanted to show you in this very simple case. So this is, okay, it's rho larger than 1. So in principle, the system must be able to recover the global minimum. It does so, but I mean, on a time scale, I mean, for a certain time scale, it remains, well, stuck, or at least it remains, I mean, very close to this point here, in which there is no information actually about the global, about the signal. And then at a certain point, it go down. So, okay, let me say, I will end with several remarks. So the first one is that if you look at this, it reminds of something that is discussed, and it's a very toy example of something that is discussed in machine learning when you look at the dynamics of machine learning. For example, Leon Botou, already in the 90s, he said, well, it's very difficult to understand training dynamics in non-convex space, but he's expecting that there will be a, let's say, what he called a search phase, in which the system is actually exploring the landscape and try to find actually the direction to go down. And then there is another, which is the convergence phase, in which really the gradient start to go down, start to become important in the direction of the good global minimum. And then you have exponential relaxation. So actually what happening here now, if you, in this very simple example, and of course, in real case, it can be very different. But in this case, what you have is that you start to go down, and when you're here, you are in a regime in which you are very close to critical points, which are almost stable. But they all have in one direction that goes down. So there is a direction to go down, but at the beginning, in the initial condition, the component in this direction is very small. So actually, you move, in this landscape, there is this direction to go down, but just, entropically, it takes time, actually, to try to, to increase the value of the component in this direction. So it's just like I'm going down here, so I have one small direction, one head direction, like which goes down. But at the beginning, I have a very extremely small component in this direction. So I just go down this way and here. And then on time scale, which are larger than log n, then I start to really have an important component in that direction. And then I go in the convex part of the landscape around the minimum. Yes?
So from your description, it sounds like the index one saddle is like making this problem of the plateau. But why not like
Sorry, the index one saddle?
Is like causing this long plateau?
No, it's more, no, the long plateau is more given by all these eigenvalues. So let me maybe draw just to be more clear. So what is the Hessian here? What is the gradient? So the gradient when you arrive here is very small. And the Hessian when you're here is it's something like this. So you have one direction here that goes down, but you have many of small ones. And so it's the fact that the system is actually lost in these very small ones. And there is this one, but okay, it takes time actually to grow, to make it grow.
So the problem is not that there is only one negative, but more that there's a lot of small positive eigenvalues?
Yeah, I would say they are both. So you have one direction, which is the one to go toward the stellium, but you have many others in which the dynamics is really taking place. So you have to wait long enough in such a way that the dynamics keep getting, let's say, information about the fact that there is this direction in order to make it grow. And actually, if you put temperature, it's even worse, because temperature is gaining entropy, and then the system is going to lose itself even more in this region. Okay, yeah.
So if it spends like order one time in each saddle point before the relaxation, so it would see like log n many like marginally stable saddle point before converging to the global minimum?
Well, not really, in the sense that you are never exactly at a critical point. You are close to a critical point, but you are not. So.
But like log n many values. Maybe.
I don't know. It's. Did you see log n many values? Okay, I will think about it. I don't know. Yeah.
I'm somehow curious that it all follows from the condition for the spherical constraint. So what if we did not put the spherical constraint and instead took lambda way bigger than 2 from the beginning? Would we still see this type of dynamic?
Lambda. So I remember that I thought about this. No, I think it's, in this case, it comes really to the fact that okay, let me use this. So you take no condition.
Say that I consider the dynamics with lambda fixed to 3.
Yeah, no, I think it's in that case that, yeah, and then you minimize the J with the, okay, I think yes, I think you would see it. I have to do it, but I think yes, I think you would see it. Because then you have an extra term, which is that from the energy, which is the sum over x square. So there is the norm square that is coming, and I think it's going to play a similar role.
Same if I do an annealing in lambda, start from very large, but regardless of the constraints, if I start from very small norm and then I less the norm.
So you fix the norm?
No, I don't fix the norm. I put a soft constraint, but I am annealing. I am that's time dependent, but in a way that is very rigid to the beginning, and then it's.
I don't know. I have to think about.
It's like starting
from 0 and then let it grow. Yeah, I don't know. It's a good question. Yeah.
Can you tell us again the intuition for why some noise will increase the time it's passed?
This actually, I will do it hopefully, if I manage to do it, I will do it in 1 or 2 lectures, because this is a message that I want to give to you in a very simple way, is that if you consider equation not like this one, a gradient flow, but you put a little bit of noise, sometimes the system can be trapped far away from the minimum just because of entropy. It's just that because noise, at least isotropic noise, will bring you around in all the possible direction that you have. So if you have to find one direction out of many, there is a kind of entropic barrier that forms, even if you don't have barrier in the energy landscape. But this I will discuss. I will discuss this in 1 or 2 lectures. Yes?
If at initial innovation I would look at the gradient direction into the direction of the global minimum and also all the cellular directions, still the direction towards the global minimum would be, the gradient would be largest, right? It's only that there are many more other directions so that the total norm of the vector
Yes. Yes, but the fact is that the gradient, the component of the gradient is increasing, but you have so many of the other ones that are of the same order and they all sum up that you don't go, except if you wait long enough that this becomes overwhelming with respect to all the other ones. Yes. So again, what I wanted to do in this way is to, start to show you some, let's say, counterintuitive maybe effect that you can find in high dimension. You see that indeed you can have this, let's say, toy model of the search phase with a convergence phase. And this, I think, are a nice model to try to, to think about some of the ideas that are around in the literature. So for example, something that we did very recently, and I think it was one of the open problem maybe, was we're thinking about the learning rate scheduling in modern machine learning. So you know that if you have convex landscape, what you should do is you should decrease the learning rate like 1/t, one of the time. This is typically in the convex, with convex landscape is the best way to go as fast as possible to the minimum. And so if you do gradient descent. And in reality, what people do is more something like that ramps up and then it goes down. And the idea behind, I think, is indeed at the beginning there is a kind of search phase in which it's good to have the learning rate high, and then at a certain point you will have to decrease the learning rate when you are close to the minimum. And so you can study actually learning, you can redo what I did with gradient descent and play with the learning rate. This is something we did with Dascoli and Refinetti this year. So, and we did it in this model, but also in complicated one, not just this one. 2022. And indeed, you find that in this, let's say, toy search phase, you have to keep a high learning rate in such a way that you explore it as fast as possible in order to reach this regime, which is the convergence. And once you are in this regime, then you decrease the learning rate, actually with the rate which is 1/t. So this is just to, tell you, all the things that one can try to understand from this simple model. So what I would like to do, yes, just one, so I will conclude just to give you the idea of the following. So this model is simple, has no bad minima, has just, 2n critical points, but after all, it's very simple. So what I would like to do is to address more complicated modeling in which you have a very large number of minima, bad minima. And so I want to show you what are the techniques to count them, to have to compute what is the structure of the minima, the exponential number of minima in this landscape, and then to explain to you what is a method which is called dynamical mean field theory that is used and developed to try to study the dynamics in this complicated high-dimensional landscape, and then put all together to tell you what happens in this case when you have dynamics in high-dimensional landscape with a lot of minima. I will always study models which are it's still far from a deep net, of course, or are models which are more close to a problem of estimation in high dimension. But I will try to, to give you at the end, on my lecture on Wednesday, the direction, where we are, where we should go, and maybe since you are students and we do research, what you should do, not you should do, what you will do to push the frontier much more. Okay, so there was a question.
How without calculating we could have guessed log n as the time?
Sorry?
How we could have guessed that log n was the end of the search phase?
It's simple, yeah.
So if you have n things, are you doing some kind of binary search as you go down?
Well, I think it's the good way to guess is just that. So as I was saying before, so there is one part of the dynamics, which is you are here, you are lost here. And then you know that there is one, okay, maybe I don't know, maybe I'm just repeating what I wrote in equation. But you have one part of the dynamics which is growing with a certain relaxation time because, well, you have this direction which goes down. And what you want is to have a time which is large enough in such a way that this takes over all the other dynamics. And in order to this to take over, this has become to order 1. And so the tau which you have here is related to the eigenvalue, so it's the lambda max t, if I'm correct. And so in this way you get it. Okay, well, we can discuss
I
it.
think we're saying the same thing, actually.
Okay.
So at least I'm going to consider it.
I guess maybe I should stop because it's time. Okay, thank you.
One thing as per this model, it would be the case that very over-parameterized models